Hi, everybody. We're here in chapter 2. The age of review is over. It is time to get into some calculus. Um, Here are the next 3 sections that we're looking at. 2.1 is going to be motivating calculus. So we're going to dip our toes into derivatives, integrals, limits, just a tiny little taste. Um, 2.2 is going to be an introduction to limits. So we're going to get an idea for what we're talking about with this new process that you may have heard before if you've done calculus before, but it's going to be new to most people. 2.3, I've labeled as limits for big kids. That one is just going to be the mathematical definition of limit using epsilon and delta. That's going to be good. Um, Today, though, we're hoping to end roughly in the middle of 2.2 so that we can pick up from there on Monday. Okay, we're going to start off with rates of change and talking about tangent lines. Here's our first example, and our book is referring to this as the velocity problem. Um, let's take a look. The big question that I would like us to focus on, and that's why I've written it down here, is how do you get a velocity function from a distance function, or maybe even better yet, how do you get any function in the first place? Here we're looking at a word problem where it says a piece of rock falls into a 256-foot deep canyon from its rim. If we ignore air resistance, we're going to do that in math class all the time. Its distance below the rim at time t is 16t squared. And it seems like they just pulled out of the thin air. And math textbooks do that all the time. But there's actually a good reason that this is 16t squared. And I think that this is as good a time as any to introduce why that ends up being 16t squared. So hopefully we're going to unravel that mystery. This question asks us to estimate the instantaneous velocity of the rock after 2 seconds and the velocity of impact when it would hit the ground. We can look at both of those things too, hopefully. But first off, I'd like to tackle the question of how do we get this function? It's just pulled out of thin air, 16t squared. Well, there is a calculus way that an acceleration function, a velocity function, and a distance function or position function are related in calculus. Because each one of these things ends up being the rate of change of the other. So hopefully, you'd be familiar with this. We're going to be measuring things in feet and seconds today, just the way it is. But if we were to measure distance in the context of this problem, the unit of measure would be feet for distance. The unit of measure for velocity would be feet per second. And so that becomes this ratio. Um, you know, Intuitively, it is the speed at which you're traveling, it's how fast you're going, it's how many feet you travel in a second. Um, and then acceleration is how fast is that velocity changing? Oftentimes in a physical system like this, acceleration happens because some kind of force is acting in the problem on whatever massive object we have. So in the context of this problem, we would measure acceleration in feet per second, or feet per second squared. And uh, the the object that is accelerating is this rock that we're dropping. Let me see if I can scooch up just a little. There we go. Okay, so we're dropping a piece of rock and it is falling. Acceleration, I just said that acceleration happens when you have some kind of force acting on the system. And in free fall, the only force that's acting on this rock is the force of gravity. So, one thing that we could do to begin unraveling this mystery of where 16t squared comes from is let's go ahead and think about this. Um, the acceleration due to gravity is approximately constant, no matter where you are on the face of the Earth. Um, and the gravitational constant, when you're measuring it in feet per second squared, is 32 feet. Normally, we orient this, down, and we might give it a negative sign rather than a positive sign. In this case, we're measuring the distance below the rim, and so we're just going to leave this at 32 feet per second. But what I mean at, a constant acceleration of 32 feet per second, it means that at time zero, we're traveling at 30, well, not we're traveling at 32 feet per second. It means that the rock is accelerating at 32 feet per second per second. Um, it's accelerating, it's accelerating, but the acceleration always stays constant at 32. And if we were to graph this, the function a of t would just be a flat line at y equals 32. Okay. Um, so acceleration due to gravity, constant over time. And you can imagine this. It's not exactly the same, but it's kind of like you're putting your foot on the gas of a car, and it's starting to accelerate because you've pushed the gas pedal. Um, the thing that has its foot on the gas is gravity, and the pedal is always remaining nice and constant so that we're accelerating at a constant rate. Anyways, to get from acceleration to velocity, we take what's called an antiderivative or an indefinite integral that we'll talk about later. But if we jump from here to here, there's going to be this relationship that's called antiderivative. And well, the same relationship is going to happen with velocity and distance. But what this means is that, acceleration and velocity are related because acceleration is the rate of change in velocity. And I'm not going to necessarily explain how I get this number. Um, we're taking an antiderivative, but this function ends up being 32t. And hopefully, when I go and list these numbers out, maybe that'll make a little bit more sense. But um, at t equals 0, when we haven't dropped the rock yet, the rock isn't moving. So it starts, we would say, its initial velocity is equal to 0 feet per second. Um, how you might interpret the acceleration is happening is that after a second, um, the velocity of this rock should be 32, because we're accelerating at a rate of 32 feet per second per second. So by the time that we get to second number one, we're traveling at 32 feet per second. By the time that we get to second number two, we're traveling at 64 feet per second. And then I believe that at second number three, we'd be traveling at 96 feet per second. And if we were to graph this one on a line, um, man, now I wish I had written that in a different color. Uh, I'll just go ahead and make a little graph here. Um, at 0, we're at 0, but then this thing is a straight line that has a slope of 32. So yeah, whereas the acceleration was just a constant function, this is the velocity function is a straight line with a slope of 32. And so what's cool is that the rate of change of the velocity function, if you're thinking about the slope or how fast this line is, you know, rise over run, all that good stuff, that 32 over 1 is the same 32 that we see as a constant y value in the acceleration function. one more time. Let's go ahead and take an antiderivative of the distance function, or sorry, the velocity function to get our distance function or our position function. In this case, again, I'm not going to explain exactly how I do this. It's going to be explained soon, in the whole scope of the class. This one becomes a quadratic function, 16t squared. And this unit is measured in feet. Initially, we are 0. Let's give this actually a different color. Let's go pink for this one. We start off 0 feet from the edge of this rim. But, as it happens, over the first second of this, we've started at 0 feet per second and we've gotten up to 32 feet per second by the end of, the first second. If we think about the average velocity over that amount of time, it actually makes sense to talk about average velocity because this one's actually a linear function. It means that if we average out going slow at the beginning of this interval from 0 to 1 and going fast at the end of this interval from 0 to 1, right in the middle of 0 and 32 is 16. And, that's actually the number that ends up being correct here. So after 1 second, we've traveled 16 feet. At the beginning of time, we weren't moving at all. And at the end of 1 second, we're actually traveling at 32 feet per second. But most of the way, we were slower than that. And so we've only accumulated 16 feet of distance up to this point, and really it's falling distance. So that's what that works out to be. And this position function actually ends up being quadratic. If we throw in 2 in that, it's 16 times 4. I should be able to do that. It's 8 times 8. It's 64. So by the end of the second, we should be we should be at 64 feet of distance traveled totally. And then at the end of 3, that would give us 9. So I think that's 144 feet traveled totally. And yeah, when we draw this one as a graph, I guess I did. Yeah, I shouldn't have drawn these in, negative time. This part should be gone. This part should be gone. It should just be positive. Because on this part, yeah, I remembered that, this part is going to be quadratic. So we get a parabola. And it's not a coincidence that, these things are growing by degree if you go this way or shrinking by degree if you go this way. There's actually a good reason for that. But calculus helps us understand that acceleration and velocity and distance are all related to each other because they're all related rates of change. One is velocity is the rate of change of distance, and acceleration is the rate of change of velocity. So there's cool relationships to be studied here, and this 16t squared was not just pulled out of midair. I want to go and actually try to answer these questions, though, especially part A. The part B would be a very similar idea. If we want to estimate the instantaneous velocity of the rock after 2 seconds, I mean, what we're trying to do is, estimate this. Right now, I mean, we did this extra work and I kind of pulled these out of thin air a little bit. We did this extra work and we're going to be expecting a number 64 here. But if we didn't have an acceleration function or velocity function or a distance function, how might we use, or sorry, we do have the distance function. If we use the distance function, how could we approximate a velocity from that? Let's go ahead, open up this GeoGebra thing, and see what we can do. Okay, there we go. Let's give ourselves a little bit of room here. All right, all of this looks very busy. Um, The idea is we are going to try to estimate the slope of this curvy thing, um, the green, quadratic function that gives us the position. We're going to try to estimate the slope at this point. So our input value is 2. I want you to notice that we are considering this thing called a difference quotient. And you've seen this before. It's just a way to calculate slope. Literally, we have rise over run. This is a difference of two y values over a difference of two x values. So one of the x values is 2, related to this point, and we can see f of 2 is 64. That's the y value related to this point A. But then I've got this other thing that says f of w and w because I've made a slider here that allows me to change this point that goes along the parabola. And you can see that as I change this point, these numbers can change accordingly, and we can calculate different slopes. Now, if I back it all the way back here and I say, you know, let's estimate that the slope here at 2 is 48. That's not an awful estimate, but notice as I bring this point W, so we're making our x value bigger, we're bringing this point up the parabola. Kind of notice how the slope of this red line starts to match the slope at this point better and better the closer that we get to this point. So, yay, this is great. We start off at 48. It's going up to 50, 60, 62, 63. Oh, and then we blink out of existence. What has happened here? Well, we put both of these points on top of each other. We're trying to calculate a slope from the same point twice. And when you do that, you get 0 over 0, which is an indeterminate form. It's a problem. It doesn't output a nice number. So there's this sense that we keep getting a better and better estimate the closer and closer that we get to 2. But if we actually land on 2, it's a problem. So here we've gotten to 1.99, and our slope is at 63.84. And I know that I'm allowing the calculator to do this calculation for us, but really, this is a slope, difference of y's over difference of x's. Hopefully that this is somewhat familiar. Notice we're a little bit under 64. If I come from this side, from the right, if I put the point all the way at x equals 3, we are, kind of way far away, and we're estimating that we have a slope of 80. That's definitely an overestimate. But as we get closer and closer and closer, we're trying to estimate the slope at this point, and maybe if I can get it down to 2.01, you can see that we're a little bit over 64. And the idea is that if this thing called a derivative exists, um, we should be able to get arbitrarily close to the actual instantaneous velocity that we want to get to. And so, yeah, if we wanted to estimate this instantaneous velocity, we could see that, from the right, we're a little bit above 64. From the left, we're a little bit below 64. It seems like we're centered on 64. And so we can take these things as an estimate. If we wanted to do an even better job, I could make this 2.0001, and then we're starting to lose, precision in the calculator. I think I probably could do a better job. Let's see if I open this up to, let's say, 10 decimal places instead. Now it will show us that we're not exactly at 64, but we're getting so close. Here we can see some more, precision there, but we're getting so close to actually having a slope of 64 the closer that we get these 2 points in. As long as these 2 points aren't exactly the same, we can zoom in and see that those 2 points determine a line, and we can calculate the slope of that line. The problem happens when we try to, like, put one right on top of the other. That's a problem. Anyways, okay, I just lost that whole thing. Let's go back to this. Um, Here are some tables from our book, and these are some things that if you wanted to just punch numbers into a calculator or you just wanted to write out numbers with your hands, um, this is what it might look like to get closer and closer to um, the point 2 in terms of our time value. Here, we're looking at the time interval from 2 to 2.09. You know, that 2.09 is what we were looking at as W on the last one on the graph. But yeah, as we get this number closer and closer and closer to 2, here we get to 2.01, we've gotten from 65 all the way closer to 64.16. So we get a better and better estimate of what the actual velocity is. And here's what it looks like to come from the left, start underneath 2, and get closer and closer to 2 using smaller numbers and going up to 1.99. Again, really close to 64. Um, so, if we want to get an estimate, all we need to do is find a couple of x values that are really, really close together. One of the x values being the, x value in question, or I guess in this case, the t value in question. Um, and, we're going to get a better estimate for the slope of a tangent line by making those 2 points as close to each other as possible. There are 2 ways that you're gonna see this difference quotient written in our textbook. In one of them, we're gonna label the 2 x values, one x value as just the letter x, and the other x value as the letter a. And normally when we phrase it this way, we would be saying that we're taking the limit as x approaches a, meaning that X is gonna be the one that we are allowed to slide around and get closer and closer to A, and A is the one that's gonna stay fixed. But, this is the form that we were looking at on that graph that I just did. Um, and so that's one way to, specify when you just look at this difference quotient, you get an approximation for the instantaneous velocity. But when we include this thing called a limit, we're going to say that, in the limit, we're calculating an instantaneous velocity when we're working with a derivative. And so the idea is we get x closer and closer to a, we get a better representation of the slope of this blue curve at the point A, the closer that we get x to it. The other way that we can look at a difference quotient, it's just really a different way of labeling the same thing. But instead of referencing 2 different points, x and a, the 2 different points that we're working with, one of them's labeled x, the other one's labeled x plus h. And this h value is really just the space in between the 2 points that we're interested in. This time, you would want to imagine h going to 0, or the distance between these 2 points going to 0. That's what this limit means. And x plus h would continue to move closer and closer and closer to this x that's staying still in this case. And the slope of this line would get better and better approximation of the actual slope of the curve over here at x. And so sometimes it's just nicer to reference kind of your home base point and how much gap you're leaving in between the 2 points that you're using to calculate slope as h. Um, but both of these ways of specifying a difference quotient are good. They're just, labeled a little bit differently. We'll come back to this too. Um, I left this in if we were interested in learning that the word tangent comes from the Latin word tangens, and it translates to touching. So I've been saying things like secant line, and I don't know if I've used the word tangent line yet, but the difference here is that the green lines that you see are called secant lines. They intersect the curve at 2 points, or at least 2 points, depending on how curvy the curve is. Um, yeah, so a secant line will intersect the curve at 2 points, but the tangent line in red just touches the curve at 1 point. So let's go ahead and I'll label this green one. Green is secant, 2 points on curve. Tangent in red just touches the 1 point on curve because it matches the slope perfectly at that point. That's the idea. So right now, theoretically, we should be able to do secant lines, no problem. All that is taking rise over run. That should be familiar slope. The tangent line, however, is where we get into calculus and we end up taking these things called limits. More on that soon. Example number 3. We are constructing difference quotients to approximate the slope of the line tangent to this graph at the point 1, 2. I didn't want to write all of this stuff and be boring right in front of you, but the idea is we're constructing this difference quotient, difference of y's over difference of x's, and this is just computation. We're putting in 2 as an input into the function, and then we're subtracting off what happens when we put 1 in as an input to this function. It ends up looking like the difference between those two y values is negative 0.4 in this specific case, and then when we let that h, or that little step off of x, be a little bit smaller, here h is equal to 1, here h is 0.5, and we would want to let h get closer and closer to 0 over time. That's the table that we see down here. But yeah, here's the difference quotients being calculated. Here's a nice table that summarizes the results. This says m sub sec, meaning slope of the secant line. And so here we see that the slope of the secant line gets closer and closer to, it looks like about 0.6. Real quick, I want to show you what this looks like in GeoGebra. There we go. Oh, hey. All right, this thing's moving. So here our point A is fixed. And this point B is moving. But here we would be taking the limit of that difference quotient as x approaches 1. So right now, for this point, x is equal to 1 and y is equal to 2. But as we move this point B up the function, we're hopefully going to get better and better approximations of the slope here. Okay, there we put it on top of each other. Things broke. But yeah, to get the best kind of approximation possible, we would want to make this as close to 1 as possible. So I might throw this a few zeros in there. I am. And yeah, notice that we're really, really close to, 0.6. And if I zoom way in on this point, maybe we can see that there is a very small difference between the point A and point B. But there is still a difference, and that means that we can calculate it without using calculus right now. We're just approximating. But notice that, in the x direction, we've just jumped up. What is this? 1 tenth, hundredth, 10,000, 100,000th millionth? 100,000, 10. Yeah. Okay. We've moved 1 millionth to the right. So h is equal to 1 millionth. And then in the y direction, we've moved up, 0.00000006. So one, there's 6 10 millions. And so the overall slope here is about zero point 0.6. It's not, exactly, but yeah. That's the idea with the limiting process. It's kind of like we're zooming in and getting a better and better approximation as we go. Um, let's keep going. Pull this back up. Um, example 4 is an instance where we can't really use these secant lines to get a good approximation of the slope at a point because, well, for an absolute value function, we have a nice slope of 1 when this absolute value function is positive or, positive x values. And for negative x values, we have a negative slope of -1. So if we try to use difference quotients here, everything from the left would be giving us a slope of -1. Everything coming in from the right would be giving us a slope of +1. I suppose you could try to make a point. Here, let me draw this so you can see it. If you could, try drawing a point over here and another one over here, you could draw a secant line there, but y there's not really a hope that this secant line means much in the whole scheme of things because we get this hard point down here where we come to a corner, and this is something that we're gonna later call non-differentiable. The derivative doesn't exist here at this point because it doesn't follow a nice smooth path. Um, and so we wouldn't be able to estimate the slope here because we just come at this from two very different perspectives. So I'm gonna erase this secant line. It's silly, but um, yeah, the slope here can't be inferred by a table of difference quotients. But the thing that hopefully we've paid attention to is that, and this is going to be true for the next example too. I'm going to underline this italicized thing. The true value of the quantity we seek can be approximated to any desired degree of accuracy through the use of smaller and smaller increments. Um, yeah, this is the limiting process. This is calculus. We're trying to get at something that we can't quite touch because if we do let the 2 points touch, we can't calculate a slope anymore. We get something that looks like 0 over 0. But yeah, it we can attain a better and better approximation as long as we are willing to use smaller and smaller increments to increase our accuracy. Okay, so there we were looking at rates of change. We were looking at slopes. The other half of calculus that we'll end up looking at is about accumulation rather than rates of change. And one way that we can measure accumulation is looking at accumulated area. So on this one, we're going to consider the graph of this function, x to the 3 halves. And what we're going to do is we're going to divide this into smaller and smaller subintervals, making rectangles to estimate the area that's here. And I will explain this nonsense after we look at the graph. Again, this is just motivation. You don't have to understand it at this point. The idea here, okay, we've got our function, and what we're doing is we're trying to use rectangles to estimate the area. And right now, I would not blame you for saying, yeah, that doesn't look like a great estimate because, if we're trying to measure all of this area that's swept out here, actually here, I could do integral. Oh, integral. And I think if I go integral of f from 0 to 1, And let's give this a better color. Boom. This is the area that we're trying to approximate using rectangles right now. And we could think of this as being accumulated as x goes from 0 to 1. Um, but I wouldn't blame you if you said that this is not a great approximation because we end up missing this chunk, we miss this chunk, we miss this chunk, we miss this chunk. It is definitely an underestimate of the area. And so there's a couple ways that we might be able to improve that. One of them is changing the rule that we're using. Right now, we're using what's called a left-hand rule because we're starting off the height of each rectangle based on its leftmost endpoint. And so we follow this function up here and we create a rectangle based on this height. And so the rectangle touches at its top left corner, the rectangle top touches at its top left corner. If we change the rule, we can change these to a midpoint rule where we look at the middle of an interval and use that to determine the height of a rectangle. And this one looks really nice, as an estimate because um, we're doing an overestimate over here, but an underestimate there, and an overestimate here, but an underestimate there. And these are not exactly the same overestimates and underestimates, but it's better than just underestimating the entire time. And if we take it one step further, we can do an overestimate the entire time, but that doesn't seem, you know, much better either. Um, Let me go ahead and get rid of the red part so that we're not running into each other. Let me go ahead. I'll take it back to the left-hand rule. So we saw that probably midpoint is better than a left-hand rule in, the vast majority of cases. The other way to improve our estimate would be to increase the number of rectangles. If we increase the number of rectangles from 4 rectangles all the way up to 100 rectangles, I want you to get the feeling that this process of increasing the number of rectangles is increasing the precision by which we are measuring this accumulation, and we get a much better estimation of the area here. This is saying that the area is, really close to zero point 0.4. Um, and this one is also saying that we're getting really close to zero point 0.4. Notice now, it doesn't make as big a difference whether we're using the left-hand rule or the midpoint rule or the right-hand rule. All of them are pretty close to zero point 0.4 now when we get up to 100 rectangles. So in this context, increasing the number of rectangles or decreasing the width of each rectangle is this process by which we're getting a better and better, more accurate estimate of the area under this curve. And real quick, I want to explain what this limit means. This is definitely some new notation for many, I would wager. But what this says is that as we let the number of rectangles go to infinity, so use more and more rectangles to approximate the area. This weird symbol, the big E, is actually called sigma in Greek, and this sigma stands for sum. So all this really means is that we're adding up rectangle areas. That's just shorthand for notation for a bunch of plus signs, really. This next one, I mean, all of these other ones are heights and widths of rectangles. This one being the output of a function. This is the heights of rectangles. This one is widths of rectangles. But I want you to notice that this limit thing shows up again. This case, we're letting the number of rectangles go to infinity. Um, Previously, we were looking at the limit as some x value approached some important other x value called a. Here we were looking as time got closer and closer to 2 seconds. Um, but this limit thing keeps popping up. And that's what we're doing in the next section. That's where we are starting our study of calculus because this limiting process is fundamental to everything else that we're going to look at. Okay, so we're going to get a real quick introduction to limits and what they are. Um, as we talk about limits, we tend to use dynamic phrasing. So earlier we looked as h approaches 0, or we looked at as x goes to a. Or, in this setting, as n grows without bound, goes to infinity. Um, in a less mathematical setting, those phrases might be like mortgage rates are expected to approach 5%, or assuming the national debt keeps getting bigger and bigger. Um, but there's a dynamic nature to a limit. And so, first off, we're going to focus in on how we would say this monstrosity of a new formula that we have. Um, and yeah, we would say that the limit of f of x is L as x approaches C. So that is the language that we would use. I- And that's a good way to phrase it. Sometimes I try to read it a little bit more left to right, and I would say something like uh, the limit as x approaches C of f of x, is equal to L. That's a way that I will phrase things sometimes just because I'm kind of reading from left to right. But saying that the limit of this function is L signifies that, you know, we're talking about a y value on either side of this equation. L is some specific y value that we call the limit. And all of these f of x values would also be y values. It's just that these y values are kind of changing as we let x get closer and closer to some specific x value called c. And so I'd like to take a look at some different limit scenarios um, and talk about the things that we might see. Um, Generally, when we talk about limits, we are using a one-dimensional domain, meaning that our domain is the x values that we're allowed to put in. And we can approach C from two different directions when we're working with a number line. Um, we can do something called a limit from the left, and we can approach C from the left-hand side. And that's what this notation is actually noting. Yeah, if you can't read that, that limit from the left looks like limit as x approaches C from the left. There's a little minus sign kind of in the exponent spot above C. New notation, but the way that we read it is that it is a limit from the left, and we would consider approaching this special value C from values that are beneath it on the number line. And very similarly, over here in blue is the limit from the right. We would take numbers that are bigger than our specific x value, C, and we would approach from the right and get closer and closer to C. And, that notation looks like limit as x approaches c from the right, and we use a plus sign rather than a minus sign. And so when we're on a number line, we can approach this point from two different directions. If you make it all the way to calculus 3, we're going to be working with uh, two-dimensional domains, and we're going to be able to take any curved path towards the point C in a two-dimensional domain. It's going to be great. But for right now, we're working on a number line, and we can approach from the left or we can approach from the right. And so these are both, left or right-handed limits. And we say that when the left-handed limit matches the right-handed limit, then we have an overall limit that exists. So in order for us to be able to approach C just overall, the limit from the left has to exist and the limit from the right has to exist, and they have to equal each other. So let's go ahead and take a look at this function, and we're going to take a look at several other functions just to get a feel for this. So if we start looking at the y values, or these f of x values, the idea is as we travel along this line, we go, or this curve, we go, and from the left, in terms of y values, we get closer and closer to which y value? Well, it's this y value L over here. And so we could say that this specific y value L is the limit from the left. And if we go from the right, we could travel down, coming in from greater x values, and the y value that we approach along this curve is, again, the y value L. And since both of those exist and they both equal the same thing, we can say that the overall limit is also L. And that's, kind of coming from both sides at the same time. Um, f of c is something that we should be familiar with, since this is a nice line or a nice curve that doesn't have any gaps or anything in it. F of c is just what happens when we plug in c. And again, f of c is equal to L here because, yeah, when we put c into the function and we map it over to the y-axis, yeah, this is the y value that we get out. It's L. And something that's cool that we will make more formal later on is that in this case, the limit from the left and the right, they match, they exist, and they equal f of c. So we call this function continuous. This one actually works. This is great. All the other ones that I have below are going to be discontinuous, so this condition isn't going to be met. But this is wonderful. Whenever we're working with a continuous function in calculus, we're happy. This is good. Let's go ahead and take a look at the next one. This is what we would call a removable discontinuity. And the idea here is that we have a little gap in our nice curve, and we've filled in that gap by replacing it with a different function value below. So we've got a gap there, we filled it in there so that we do have we do have values for the entire domain, which is cool. But yeah, the function value here is going to be different than the limit. Let's go ahead and take a look at the left-hand limit real quick. So if we go left-hand limit, I think I was doing that in pink. Left-hand limit, left-hand limit in the x direction, that's L. This one I think I was doing in blue. So if we approach C from x values that are bigger than it, we would also go to L in terms of our y value. And both of those exist and they agree. So the overall limit, is equal to L. And so, both of these at the same time, both approaching the same y value. However, f of c here is actually the position where this little dot is. That's where the function's defined. So this is actually L divided by 2. It's half of L. And since these two things are not equal, f of c does not equal the limit, we would say that this function is discontinuous at this point. Um, and you can see that in a very like colloquial sense, you can't draw this curve without picking up your pencil. Like, in order to draw this, you would have to stop, you would have to draw another dot, and then you'd have to keep going, and you would have to pick up your pencil on this one, whereas no pencil picking up here. All right, couple more. We'll try to continue to do this at a decent pace. Here's a gap discontinuity. Here we have not filled in that gap. So let's, if you want to take a shot at filling these in on your own, feel free to work ahead of me. That's totally fine. Um, but let's go ahead. From the left, it looks like L. We'd be going this way. From the right, again, it looks like L. From the right, that's all good. And that means they exist, they agree, the overall limit exists, and it's L. In this case, the difference is that f of c does not exist. We'll use that DNE for does not exist. It's undefined. You could write that too. But yeah, f of c is not defined on this function. And, for that reason, again, we are not continuous. Moving on to the next one with an asymptote. Here, if we're doing a limit from the left, it looks like our y values continue to increase without bound as we, approach the x values closer and closer to c. So in this case, we would write the limit from the left looks like infinity. Technically, this limit doesn't exist because we don't approach a specific y value. So let's go ahead and write technically, nope, technically, the limit does not exist. Just like in Mean Girls, the limit does not exist. But we still, because we don't reach a specific y value, because we don't approach a specific y value. We don't approach a specific y value. But we still write the limit from the left equals infinity because that's a more descriptive way of writing what's happening there. It's saying that these y values continue to grow without bound. So we are going to use this notation. Technically, though, this limit doesn't exist. For the same thing, as we're going from the right, we'd be approaching c from the right and x values. And again, our y values would be growing without bound. So we'd write the same thing. And again, technically this right-hand limit doesn't exist. Technically, the overall limit doesn't exist either, but since the left and the right hand matches our notation of infinity, we would write infinity there as well, because that is a description of what's happening from both sides of this function. F of c here does not exist. That's off at infinity. It's not any real number. And, since neither one of these really exist, this is definitely not continuous. That limit does not equal f of c. Okay, two more, and then we're going to be pretty close to the end for today. This is what we call a jump discontinuity. So you can see that, yeah, there's a jump there in the y values. From the left, I don't know, let's give this, I don't know, let's call this one L2, and we can call this y value L1 for different, limiting values. But as we come in along the left and we approach C in the x values, we approach L2 in the y values. And I don't know, maybe I should give this a subscript. That would probably be a nicer way of writing it. Cool. It approaches that y value. Um, Coming from the right, we'd be traveling up this line and we would be approaching the y value of L1. Since those are two different specific y values, we would say that the overall limit does not exist because L2 doesn't match L1. F of C technically exists here. F of C is L2 up there. That's the filled in dot. But since we don't have a limit, we can't call this continuous. And again, it corresponds to the idea that we would have to pick up our pencil to draw this function properly. Okay, last one is a weird one. It's called an oscillating discontinuity. And the idea here is that we keep oscillating up and down and we never settle in on one specific y value. Imagine this continuing to oscillate infinitely as we get closer and closer to C. We might look at, this kind of a function graph on GeoGebra so that we can zoom in and out soon. Um, so from the left, what's going to happen is we're going to start approaching in our x values. We're going to go up and down, up and down, up and down, and we're never going to settle down. This limit from the left won't exist because it never settles down. Same thing from the right. The limit won't exist because we'll keep bouncing up and down. That definitely means that the overall limit does not exist. F of C in this case probably doesn't exist. And there's no hope of it being continuous if all of those things aren't really well defined. There's a chance. Yeah. Most of the functions like this, if you were going to try to specify a value for f of c, you would have to like put it in the definition of the function. It would have to be defined piecewise rather than it, being just a natural part of the function. Anyways, those are some different scenarios for limits, and hopefully that gave us a sense of limit from the left, limit from the right, sensing when they match, all that kind of good stuff. If you have any questions, definitely let us know. We're getting close here. I think I had imagined stopping right here. So we've got two more examples. First one, deduce the one-sided infinite limits of this rational function at its vertical asymptote without graphing the function. Okay. So let's do this. F of x equals 1 over 3 minus x. We would be able to know where its vertical asymptote is that's when the denominator of this fraction is equal to 0. So asymptote at x equals 3. And what they're asking us is we're trying to decide the one-sided limit. So we're taking a limit from the left and a limit from the right around the x value of 3. So for the left-handed limit, let's go ahead and get that pink. limit as x approaches 3 from the left of 1 over 3 minus x. That's the limit that we're trying to evaluate. We're hoping to be able to put, some y value in this box, but we're at a vertical asymptote. This thing's either going to go off to positive infinity or off to negative infinity. And really, it's just going to be our job to figure out which one of those it goes to without graphing the function. And the idea here is we can use a similar technique to what we were doing when we were calculating those tangent lines. If we just scooch in and try to get a value of x that's really, really close to 3, but not exactly 3, we should be able to make something that makes sense. If we just plugged in 3 to this function, we would get 1 over 0, and that's nonsense. But if we plug in something like 2.999 or something like that, let's look at f of 2.99. That would be 1 over 3 minus 2.99. That would give us 1 over 100, which is actually equal to 100. And so, if we continued to add more nines at the end of this decimal, this would continue to get squished out and we would get bigger and bigger numbers. The idea is that this one ends up going to positive infinity. The closer that we make this 2.99 number closer to 3, the bigger the value this overall fraction will get, because we're going to be dividing by a smaller and smaller number. Likewise, if we go from a limit from the right, limit as x approaches 3 from the right, here we don't know what we're going to put in, but we do f of 3.0. Yeah, here, let's make this one interesting. We'll go 0, 0, 1. I put an extra 0 in. It's super interesting. 3.001. This is going to be a negative number. It'll be 1 over negative 0.001. And that'll be negative 1,000. And so likewise, as we make this number closer and closer to 3 from the top, we would get closer and closer to negative infinity in the y values that we continue to create. It would continue to grow without bound in the negative direction. And so I know that we did this without graphing it, but calculating these limits would actually help us sketch a graph, even if we didn't have one handy. We know that we have an asymptote at x equals 3. And from the left, we saw that this function was going up to positive infinity. And from the right, this function is going down to negative infinity. So the overall graph would look something like that, just as a sketch. Cool, cool, cool. Last problem. Let's use this function h to decide whether the given one-sided limits exist. Again, we've talked about these. Maybe go ahead and try to see if you can do these on your own for, a few seconds. Maybe take 60 seconds or something. Go ahead and pause me. But try to see if you can work these ones out, and then we'll talk about them, together. Or I'm really just going to talk about them right now. Okay, so yeah, let's just use blue here. The limit as x approaches 0 from the right. As we approach 0 from the right, it looks like we're in this oscillating part. I would say that that right-hand limit doesn't exist because the y value is just going to keep bouncing up and down. Does not exist. For part B, we're going to 2 from the left. So we're over here, Our y value looks like it is approaching 1. So that would be the limiting value there. That's the y value. Um, C, as we go from 2 to the right, here let's go with a yellow. Here we're traveling along the function there, and we get to a y value of 2. Um, let's use a green. Here we're looking at 2.5 from the left. So here we would be going closer and closer to the y value of 3. Here we're going to 2.5 from the right. And so let's use purple and go this way. Again, we would be approaching um, the y value of 3. And for this one, we're approaching 3 from the left. So in our x values, we're getting closer and closer to this vertical asymptote. We've got, I don't know, let's use red. Oh, let's use orange. Orange going off to infinity. We would write infinity, know that this technically doesn't exist because we're not approaching a specific y value. But yeah, that's just some practice. We'll get some more practice on our activity and maybe on our homework too for these limits. So, we'll get some more time for practice there. On Monday, we will look at limits at infinity. So we'll let x go to infinity or x go to negative infinity and think about what happens there. Um, we'll look at some crazy things, that graphing calculators do with some limits when you try to zoom in. And we'll look at this mathematical definition of limit using new Greek letters like epsilon and delta. It's going to be great. So looking forward to Monday. I hope you have a wonderful weekend. Um, we'll see you then. All right. Bye. Here, I'm gonna try to this and that and the call. See ya.